Welcome and thank you for downloading the SteerDuff podcast.
You and not Professor Bijl. She's again hampered by unwilling leg, and they don't have to take it off, but it hurts very badly. She's got what they call in Dutch een zweepslag. Yeah, it's very bad. I don't know how you call it in English, but it's something to do with a muscle and some rupture of a muscle. So it's very painful. And you know, she's the type that she can not sit still, but she has to. So there's the stress part for her. But anyway, she asked me to fill in for her, and I will gladly do that, of course, because these are nice subjects for aerodynamicists. And she asked me to rehearse a little bit and then take it on where she left, namely with the wings. Up to now we've seen some parameters, some key features of airfoils to give lift, and by generating lift the byproduct is of course drag, which is unwanted, but it's there. You have to cope with that. So just to quickly go through this one more time to be sure that you also understand what we're talking about. The typical example of a pressure distribution, CP. In general, we do not put here CP minus, but CP, and then negative is up, so that you see here 1. Of course, this is the same, this combination, but generally you would see -4, -6, and so on, and here you would see 1. This is the upper side, this is the lower side, because we have negative pressures here. In general, we say upper side of the airfoil, but also suction side, because of the low pressures there. And this is, of course, if this is the suction if this is the suction side, then of course this is the pressure side. Yes, okay. The definition of the pressure coefficient. That is the pressure somewhere, the static pressure somewhere on the airfoil, on the object, minus the pressure, the static pressure, far in front of the airfoil in this case. So infinity divided by the dynamic pressure, half rho v squared infinity. This is the pressure coefficient, compressible and incompressible. Doesn't matter, this is the definition. Right? Okay. And if we look at this here, where the CP is 1, that of course is the stagnation point. Doesn't matter if it's compressible or incompressible, that is the point in the pressure distribution where we reach the total pressure, because the velocity here is 0. Right? So if we look at Bernoulli's law, P plus half rho v squared is constant. This constant is called the total pressure, PT. And if this v squared is 0, then we have P is PT, which means that the P here, as when the CP is 1, is the total pressure. P is PT, and if we put PT here, then PT minus P infinity divided by Q infinity is Q infinity divided by Q infinity, that's 1. Right? So in the stagnation point, CP is 1. And it's called the total pressure. And doesn't matter if it's compressible, it's total. And when we stop the flow, the same can be said from a reservoir, for instance, where the velocity is 0. If you remember the compressible piece about a wind tunnel, for instance, supersonic wind tunnel, then you have a big reservoir, you pump it up, high temperature, and then you release a valve, and then it's flowing to Mach 1 and further. And then in this reservoir, V is 0. So in this reservoir, we have the total temperature and the total pressure. Right? Okay. I will come to that later, maybe. Okay. No. This is also in the book. This is just an example of the book. Right? So, okay. So, talking about pressure distribution, right? You've seen this before, but I'll quickly address it one more time. We would like to know the normal force. And the normal force, by definition, is the force perpendicular to the chord line. Right? Lift, by definition, is perpendicular to the velocity. And drag is, of course, in the direction of the velocity. And the normal force and the tangential force, normal force is perpendicular to the rotor plate, to the chord line, and the tangential force is parallel to the chord line. Okay. Now we have this piece ds of the contour here. So this piece here, that's right there. There works a pressure on it, of course, perpendicular to this surface part. This pressure here. And if we look at this, this piece here, we have dy and dx. And this dx is ds cosine of theta. We have all kinds of angles here, and the angle that the surface makes with the chord line is theta. So ds cosine theta is dx. But if we would like to know the normal force, then we need to have a part of this normal to the chord line. And that is, of course, p cosine theta. Right? The force here moves like this, and if we want to have a force that is perpendicular to the chord line here, then that is p cosine theta. Right? So if we look at the normal force per meter span here, then we have to integrate all these pieces ds, from the leading edge to the trailing edge, and this on the upper surface and on the lower surface, and we've subtracted the two, right? So p lower cosine theta ds minus p upper cosine theta ds. And here you see cosine theta ds, which is dx. Dus actually we have the normal force is the integration of 0 to c p lower dx minus p upper dx. So in fact, it is the area between the upper and the lower pressure distribution that we integrate. So the bigger this area is between the two, the bigger the normal force is. Right? And okay, we are used to coefficients, to using coefficients instead of forces. So we divide the normal force by half rho v squared c times 1. Yeah, so that's the area c times 1, because it's per meter span. So that's n divided by q infinity times c. Right, and if we put that here in this equation, then it's cn integrated from 0 to 1 dx over c, pl minus p0, and you see directly that these are pressure coefficients. If you put this in there, if you put in p infinity, then these are pressure coefficients. So the normal force coefficient is the integration between the CP's, up and low, over the chord. In this case, dx over c. So this is the normal force. Now here you see that here we have an airfoil. This is the chord line. This is the velocity. So per definition, this is the angle of attack. We have a lift and a drag force. Together they form a resultant force. Here it is, this resultant force. And this resultant force can also be made of a normal force perpendicular to the chord line and a tangential force. Right? You see there's a T. This is the definition of T is positive in this way. Also as drag is positive in this way. So T is negative here. So there's on the nose, more or less, there's a sort of suction force on this airfoil. Oh, okay. And if you want to use these forces and abstract T and N from L and D, or vice versa, then you can use. You've seen this before, because I think in one of the first lectures on the forces on an airplane. You've seen this also. And it's not different here. Okay, so if we have the normal force and tangential force is, of course, integrating in y direction, right? So that's a little bit more difficult. But if you do it as a good integration from the minus y until the plus y in y direction, so perpendicular to the chord line, then you have this t. If you write it down as coefficients, then of course you see here Cn cosine alpha minus Ct sine alpha. And for small angles, cosine alpha is about 1 and so on. So then Cl is about Cn is about here. So for very small angles, and generally you have that when you talk about airfoils in wings, you know, then the angle of attack in cruise anyway is not so far off from very small angles, because there the CD is low. Okay. Well, if we talk about compressibility, I mean, everything up to now was subsonic, you know, and we have a certain CP there on the airfoil. And if we now increase the Mach number, then at first not so much happens. It goes a little bit up, the CP. In fact, if you look at it from this perspective, then it is fairly constant here. Nothing happens until it goes up here. And this has to do with the fact that the compressibility comes in. And the gentlemen, Prandtl and Glauert, they found out that the CP for a compressible case can be calculated from the incompressible case by dividing the CP by the square root of 1 minus m infinity squared. This is also called beta, the CP 0 divided by beta. So this is incompressible and this is compressible. Right, you see that CP goes up. If m goes to 1, then this is getting smaller and smaller, so CP goes up. Here you see it. And with CP going up, then also the velocities go up. Right? Well, here we have what we had before. The CL is about, because it's small angles, is about the integral of 0 from 0 to c of this divided, all these CPs divided by this Prandtl-Glauert rule, dx. And because this is a constant, for one certain Mach number, this is a constant, so we can take it outside the integral and put it like this. And of course, this is the old CL0, right? CL0 is this. So also, just like the CPs, we can write CL compressible is CL incompressible divided by beta. Right? And if you look at the CL alpha curve, then you see what happens. If it is incompressible like this, then if you increase Mach number, then the lift gradient will increase as well. So the increase of lift with 1 degree will get bigger. This all as an effect of the fact that the CPs get up if you approach Mach 1. So the lift gradient is getting steeper. Okay, but if we look at a certain airfoil, right, and then we look at the velocities at the upper surface. Upper surface give super velocities, higher velocities. Pressure goes down, velocities go up. So if we have an approaching Mach number of 0.3, that's somewhere on the airfoil because of the form. It's simply the form that gives you the velocities there, and somewhere the peak Mach number is 0.44. If we increase the Mach number, then also here the Mach number will increase at the thickest point, where the velocity is highest. There you will see also that the peak Mach number is increasing. 0.6, and here it is 1. And this is what we call the critical Mach number. So the critical Mach number, by definition, is the Mach number of the incoming stream for which somewhere on the airfoil Mach is 1 is encountered. And that usually is next to the thickest point, of course, because there the velocity is highest. Well, and then, of course, it depends all on the form of the airfoil, right? So if we have a very thin airfoil, then the velocities, the super velocities at the upper surface are not so high. And if we have a very thick airfoil, then of course these velocities are much higher. And that also gives you a clue about how they would behave if the Mach number goes up. Here you see for a thin airfoil, then somewhere the minus CP, so this the lowest CP is minus 0.5, somewhere here on the thickest point. So if you would increase the Mach number, then this would be the CP. If you have a medium thick airfoil, this is, say, what is it, 9%, 10%, and this would be something like 14 or 15, and this would be 17 or 18, right? And the moment you make it thicker, then also the CP goes up. And the point where Mach S1 is reached comes closer, is reduced, comes closer to 0, of course. Because in this case, the supervelocities are so high that Mach 1 is earlier encountered than in this case. So there is a relation between the thickness of the airfoil and the critical Mach number. And you see this line here, and then we'll look at it closely. If we look at the critical pressure coefficient, right? We'd like to know an expression for this critical pressure coefficient. This curve here is depending on the airfoil, right? But this is depending on compressibility in general. So there should also be a general equation. So let's derive it. The definition of the pressure coefficient, Cp is P minus P infinity divided by Q infinity. If we take P infinity divided by Q infinity out of the brackets, then we end up with P divided by P infinity minus 1 in between the brackets. Right? It's the same Cp. Nothing happened yet. The dynamic pressure, here, this Q infinity, is half rho infinity V infinity squared, is half rho divided by gamma P infinity, and you know where it's going at, because this gamma and this rho divided by P has something to do with the Mach number. If you remember that the velocity of sound is the square root of gamma RT, is the square root of gamma times P divided by rho, by the density. So we're going in this direction. We write this as in a form where gamma comes in. And so if we write it like this, then this is V squared divided by Q P infinity divided by rho infinity. And this here is the velocity of sound squared. Right? So you fool around a little bit with these parameters here, and then you find that there's a velocity of sound here, speed of sound. Okay, so this Q infinity is half gamma P infinity times Mach number. Okay, so if we fill it in here, for isentropic flow we found P0, and it's P0, there's somewhere in the flow velocity is 0, P0 divided by P is this. If we use this, it's P infinity, right? So this is P0 divided by P. This P and this M belong together. And this P infinity and this M infinity also belong together. And this is made by the fact that somewhere the velocity is 0. If we divide these two here, now we needn't worry about somewhere the velocity is 0, because we have this equation here, and if we substitute this one, this P divided by P0 here, by Q0, if we put that in this here, this is the expression for the critical CP. And then these P infinity falls out, so this is the expression for the critical CP. You don't have to learn this by heart. We will give it to you if it's needed. But you should have seen it, because if you put in M as 1, then this is the one, this is the CP critical. So if you put in M as a certain value, then you get CP. So here you see it. This is M here, relation of M with CP critical. So that is the line here. Oh, this is that line here. So this is airfoil dependent here, and this is the line for the critical CP as a function of the Mach number. Okay, and here it is. And simply, by intersection, you will find the critical Mach number for a certain airfoil. If this is the CP for a certain airfoil right here, and this is the critical Mach, the critical CP as a relation with the critical Mach number, then here at the cross, there at the crossover here, there is the critical Mach number. Okay, so here we have the Mach number, and here we have the drag coefficient. Well, you see what happens is that here at low Mach numbers, there is a flow here over the airfoil, nicely attached. And then we reach the critical Mach number here, so somewhere on the airfoil, the Mach is 1. And then it takes some time, and then suddenly the CD increases rapidly. Very high increase, so 5 times the original value. And this is where it starts, which we call drag divergence. The Mach for drag divergence. And you see what happens, it diverges in the sense that it's getting bigger and bigger all the time. And how is that possible? That is possible because a shock develops at the upper surface, or at the lower surface, or both, depending on the velocities, of course. A shock is there, and over a shock, the pressure goes up. That's what you hear, of course, when there's an airplane crossing the Mach is 1, then you hear sudden shock, you hear something in your ears. You feel something in your ears, and that is this pressure increase. So this pressure increase is causing separation. Pressure increase means that the molecules that will like to flow along the contour are pushed back. Right? So it separates. And the separated boundary layer is giving you very high drag. So that's why it's drag divergence. And because of this high drag, and in the old days people talked about the sound barrier. Because you need a lot of fuel, a lot of thrust to overcome this increase in CD. To get to this point here, to the higher Mach numbers. So that is why it was called a barrier. Not only because of this sound that it makes, this noise that it makes, but definitely because of the increase in CD. Now, if we go any further, then we have a shock, a bow shock. So that's a shock in front of the airfoil, not on the airfoil, which means that there is a totally different flow over the airfoil than here, and then the CD goes down again. So, and of course, if you are developing an airplane, this, of course, is worrying. If you reach this here, then, of course, you lose a lot of fuel without any very big velocity increase. Right? So you should avoid that. Here, in between, nothing significant happens. I mean, this here is, there's locally, somewhere locally on the airfoil, there is a sort of Mach region for Mach is more than 1. Here you see it. If the Mach number is smaller than the critical Mach number, then you see here, this is just subsonic flow. If it's between the critical Mach number and the drag divergence, then locally you have supersonic flow, but without any repercussions. And then if you reach the drag divergence here, then there is a large shock here. Here is a Mach number smaller than 1. Here it is bigger than 1. A large shock with an increasing pressure and a separated region. So, and this should be avoided, of course. So the idea is that you develop airfoils that have a lot of lift, and lift is associated with suction. So very low pressure, but low pressures mean high velocities. And high velocities mean high Mach numbers on the airfoil. And that is something that should be balanced very importantly. So that was the start, when people started to realize that was the start of the development of supercritical airfoils. And here you see what really happens. They're rather flat from the upper surface. And they are so flat because of the fact that you do not want to have high negative CPs here. So in this case, the critical CP is superseded here, but not to a great extent. Right? So there is from this point to that point here, there is supersonic flow on the airfoil, but without very high repercussions on the CD. Just because of the fact that the super velocities here are kept to a minimum. And of course you need some strength and stiffness of your wing, so it should be thick. And then, of course, you add thickness to the lower surface. Right? Because you need some building height for the strength and the stiffness of the entire wing. Okay, so a conventional airfoil, in this case this one here, a conventional airfoil that is in a supersonic flow, or at least between the critical Mach number and the drag, beyond the drag divergence Mach number, will have a shock here with a separated boundary layer. And like I said, shock means an increase in pressure. And since we put a negative pressure up, the curve goes down. So what you see here is a certain sudden drop in the CP, the negative CP, so an increase in pressure. But it comes significantly over the sonic CP. And in this case, you see that over a large part of the airfoil, we have a supersonic flow. There is a small shock here at the end, and then this is the CP. And of course, then this is the CL remaining. There could be the same CL, but this one has significantly more drag than this one. Of course, it depends on many parameters of the airplane, right? So it's the choice of the airplane manufacturer, the aircraft manufacturer, what to do. So they develop their own supercritical airfoils. So it's very difficult to find the airfoil that's in the wing of the A380 or the 747, because they just keep it to themselves, because this is a long process. I mean, it involves all kinds of development of analysis codes. It involves wind tunnel measurements, very expensive, and stuff like that. So they keep it to themselves. Right. Okay. Finite wings. Up to now, we've seen that. Yeah, there's a question. Right. Yeah. Yeah. Okay. Up to now, we've seen airfoils, right? There's an airfoil in the wing, but if we talk about airfoils, then we assume an infinitely long wing, so without an end, at both plus infinity and minus infinity. So that is an airfoil, two-dimensional. But in fact, of course, what we use as wings, they are three-dimensional. So there is an end, there's a tip, and there's a root. Right? So, and that behaves a little bit differently. So what we see here is a wing. If we look at this picture here, then we see this airplane here, and from the wingtips we see these vortices coming off. Right? And what we see here is that this is an angle of attack. Here we see the tip vortex developing from the tip. And why is this happening? Well, simply because we have a low pressure on the upper surface and a higher pressure on the lower surface. And at the tips, the lower pressure wants to go to the higher pressure, or vice versa. But in this case, it goes like this. The higher pressure goes to the lower pressure. It just moves around the tip. And this makes a tip vortex, and depending on the loading of the wing, so how much negative pressure you have there, the strength is determined. And also on the form of the tip. You can do something with this process of moving from the lower surface to the upper surface. You can direct it a little bit so that you can suppress the negative effects of it, because it has negative effects. We will see that in a moment. The fact that it's not an infinitely long wing means that you have extra drag. I cannot show you this one. I'm sorry, but it's yeah. I'll promise if you come to the studio classroom, then I will show this video. Okay. So what happens really is, in fact, that here we have this vortex, and it induces a downward velocity, an induced velocity here, at the position of the wing. Because of the fact that it goes like this, there is a velocity here going down. So if you look at the velocity far upstream, then the direction of the velocity is like this. But at the wing itself, because of the fact that these vortices that come from the tips induce a velocity field going down, we have a different velocity here. In fact, a different velocity vector. So also a different angle of attack. Okay, let's look at the development of this angle of attack change. Right? Here we have the airfoil. This is the chord line. And by definition, if we have this as a velocity vector, this is the geometric angle of attack. Right? By definition. So, by definition, the lift force is perpendicular to the velocity. So there's the lift force. And this is, again, this is parallel to this chord line, so this is also the angle of attack. This is the angle of attack, and this is the angle of attack. Now, because of the fact that we have a downward velocity pushing the air down at the position of the wing, then this is the new velocity vector, right? And that is this one. So this one is parallel to this one. So the local flow direction is not this angle here, but it is this angle here. No, I'm sorry. This is the local flow direction here. So what we see is that when we now want to look for the lift force, which is perpendicular to the velocity, then this is the velocity vector direction, and the new lift force is pointing in this direction. And the angle between these two is the induced angle. What you see here. This is the induced angle. And what was left is the effective angle, right here. And in fact, if we look at this lift vector here, then this lift vector has a component in the original velocity direction. It has a component in this direction and a component in this direction. So in fact, it rotated, this lift vector counted a little bit, it rotated in the backward direction, giving a force here pointing in the drag direction, in the original drag direction. And we call this an induced drag. And this rotation of the lift vector is due to this velocity here. Okay. And this induced drag, because it's in the drag direction, we call it induced drag. And of course, that dy is L sine alpha I. Right? But since the angle of attack is very small, and sine alpha I is also very small, then we can write sine alpha I is alpha I. So this induced drag, which can be quite significant, this induced drag is di, L times alpha I. So because of the fact that there is an end to the wing, we have a wing vortex. This wing vortex on both sides induce a flow field also going down. And because of this flow field going down, then the local angle of attack that the wing sees is different, is an effective angle of attack. Okay, so we would like to know when is, I mean, it's a drag, of course. I mean, and you should reduce drag. So when will this induced drag be the lowest? And that is, the induced drag will be the lowest if we have an elliptical lift distribution. And that's why I showed you the pictures in the beginning of the aircraft. They have a elliptical wing. Because lift, the force, is not only CL, it's also chord, right? Because surface. So if you play around with the chord, then you can also do something with the lift vector, with the lift force. Let me show that. Obviously, the I has something to do with the lift, right? And the lift force is CL times half rho V squared times S. Right? And in this S, we have the chord times, well, times something. Depending on the span and whatever. Right? But there is a chord there. So, if you want to have a certain distribution of lift in span-wise direction, then you can certainly do something with the CL, so a certain airfoil, but also you can play around with the S, so with the chord, right? So that's why you can shape your wing in such a way that you will have this elliptical lift distribution like here, and then over the entire span of your wing, the velocity, the downward pointing velocity is constant. And in this case, when this is constant, then we have the lowest induced drag. From incompressible flow theory, we find this one. So it's a not so complex theory, but it goes beyond this lecture. Alpha I is CL divided by pi times A. And A is the aspect ratio of the wing. And it is B squared divided by S, aspect ratio of the wing. So, if we put this in the equation on the previous slide, then we see CDI is CL squared times pi times the aspect ratio for an elliptical lift distribution. If we do not have an elliptical lift distribution, then we need a correction factor. Yeah, and this is a nice picture, of course, but it comes a little bit too early to my sense, but I will show it anyway. I was a bit surprised because I need a slide in front of this, but anyway. Here you see, of course, it looks like a sort of heart, you know, but you see that it also moves down, this one. So this is the big vortex here, coming off the wings here. And there's another one, and it's not the same, because here you see the wing tips here, they're a little bit different, not the same. And here you see it's long gone, but it's still there. And that is what you see on airfields as well, that there should be a certain distance between landing aircraft, because these tip vortices can be very, very strong and very persistent. They are there for a long time. And if you have a very light aircraft following a very heavy aircraft, and then you just flip, right? So there should be some distance to have these vortices diffusing a little bit, because they are so very strong and persistent. And of course, aspect ratio has something to do with this. Aspect ratio. Higher aspect ratio means a lower induced drag, right? So here you see it for a sailplane. It is of eminent importance that the drag is very low, because if you have a high drag, then your sink rate is very high, right? So you need a high aspect ratio. That's why the B, so the span of these sailplanes, is very long, so that the aspect ratio is high. Well, and here, of course, this is the Mirage 2000. It's very high induced drag, because the aspect ratio is 2 or 3 or something. Okay. Span efficiency factor. So if we do not have an elliptical lift distribution on the wing, then we are off the lowest induced drag. And then we put here an E, the Oswald factor, which means that it's the span efficiency factor. And it gives you a clue how much the lift distribution differs from an elliptical one. Of course, E is 1 for an elliptical distribution, and generally, depending on the wing aspect ratio, of course, it's about 0.85, 0.9, something like that. So if we look at the total drag of a wing, then now it's not only the profile drag, and profile drag consists of pressure drag and friction drag. It's not only the profile drag, but it is also the induced drag as a result of the fact that it's a not infinite wing. Okay. We'll see each other after the break. To reduce the induced drag, this is a way of using the same airfoil, so the same CL at a certain angle of attack, but then shaping the wing in such a way that the lift distribution comes close to the elliptical lift distribution, in such a way that the drag goes down, the induced drag. Right, I went to my office and I took the video from my laptop, and here you see 2 smoke columns, and this is what happens, you know. You see that it goes down. These vortices, they not only influence the entire flow field, but they also go down themselves, because the whole flow field behind the wing is sinking. Right, so it is a very instructive video to see what really happens, and it's not localized. I mean, you can see, clearly can see that this influences the entire wing. So it's not only localized at the tips, but because of the fact that there is friction, of course, if it rotates here at the tip, then because of this movement, all the air is moving around. Yeah, there's a question here. Lift distribution.
But what do you do in the middle? There's your fuselage, so with no lift there.
Yeah, there's a question saying that if you have an aircraft, then of course you would like to have an elliptical lift distribution, and in the middle there's this big hole in the wing, and we have to store passengers as well, of course. So the fuselage is there, and that doesn't contribute to a lift distribution. That is true. So, in fact, you cannot entirely, for a jet, you cannot entirely get this lift distribution, this elliptical lift distribution. So you will always have something like an Oswald factor of a certain value. But this is quite instructive. Okay. So now you can more judge these pictures as well, right? These are more or less descending downwards. This is quite, well, it's not a very big plane, but it's a general aviation type of aircraft, and it has a very strong pair of vortices. Okay, here's where we stopped. So the drag of a wing here is the profile drag plus an induced drag which depends on the CL, the lift coefficient of the wing. So not of the airfoil, but of the wing here. Pi times the aspect ratio times E. And for an elliptical loading, we have E is 1. Now, what happens to the basic lift curve of an airfoil when you put it in a wing? We've seen that there is an extra drag component, and we would like to know what happens to the lift curve slope. I mean, we've seen that lift curve slope is affected by the Mach number, right? So if you have a higher Mach number, then the lift curve slope goes up. And this might also influence the way lift is generated by a wing. When you put an airfoil in it with a certain lift curve, then this will change because of the fact that you put it in a wing. Now, so what we see here is, again, this airfoil with the chord line here, the geometric angle of attack. Here we see the induced angle of attack. So this is the angle that exists because of the fact that you have downwash behind the, or at the position of the wing, you have downwash. And what you see effectively, what this airfoil effectively sees is this angle of attack. So geometrically, for the wing, this is the angle of attack. But what the airfoil sees, because of this velocity vectorial addition, is that this one, alpha effective. So that's alpha minus alpha I. Okay. So here we see it. The local effective angle of attack is this one. So that's what the airfoil sees. So if we would like to look in tables how high the lift would be of an airfoil, then we would look for this alpha here. That's what you would measure in the wind tunnel, more or less, right? Okay. So if we look at this alpha I again, this one here, then it says CL divided by pi A E1, and this is in radians, people. So if you want to put this in angles, then you should multiply it with 57.3, 180 divided by pi, right? Okay, this is angles. And usually we use it in this form, of course, because we seldom talk about radians, but in general we talk about angles. Degrees, sorry, angles, degrees. Okay. If we would have an infinite wing, so an airfoil, right? Then we would have this lift curve, an infinite wing. And in general, when we talk about airfoils, then we write the CL with a small l, and if we talk about wings, then we write the CL with a big L, with a capital L. Okay. This lift curve slope is A0. DCL, d alpha, A0. And of the finite wing, we look at the geometric angle of attack, and this is A. Now, from thin airfoil theory, we find that A0 for a very thin airfoil, we find that A0 is 2 pi. Radians, right? Radians, 2 pi. So this is this A0 also for airfoil thicknesses that deviate a little bit from thin airfoils. It's about 2 pi, right? And you see, if we have a finite wing, then the CL0 is of course the same, because when we have CL0, then there is no induced drag. So the CL of the airfoil is the same as the CL of the wing. There's no induced drag, because CL is in the formula of induced drag. Now, let's do it slowly. Eventually we'll come to something like this, and this derivation you do not need to know, but I have to show it to you anyway. The effective local of angle of attack. So this is what the airfoil sees. So for an arbitrary loading, here we see that alpha I is with an Oswald factor here. This is the same as DCL, d alpha minus alpha I, right? So this is alpha effective. Then we do alpha effective is A0. If we integrate this, then we get CL is A0 times this difference plus a constant. Or I write it like this. This alpha I is the same as this one. Right? So this constant can be taken from this one, and then we have here this expression of the CL of the wing. And if we go further, we do DCL, the alpha, then we get this. And this is the only thing that you have to know. Is forget the derivation. This is what you have to know, because what you see here is the lift curve slope of the wing as a function of the lift curve slope of the airfoil that you put in it, namely A0. Of course, there's an aspect ratio there as well, because it depends, all this drag, induced drag, depends on the aspect ratio, and on CL, of course, but here is the aspect ratio. So if we have an infinite wing, then of course it is 2 pi, because then A0 is 2 pi. Infinite wing, so this is 0, right? So is it A0 divided by 1, and A0 is 2 pi, so then DCL, the alpha, is 2 pi. So that's the airfoil, thin airfoil. For finite wings, like Fokker 50 type, then we see that DCL, the alpha, is something like 1.71 pi. So that's considerably lower, right? And if you have A is 5, then again that is a significant amount lower here, 1.43 pi radians and 2 pi. So this wing lift curve slope can degrade quite a bit. There's a question. Why is A0 2 pi? That is thin airfoil theory. It goes a little bit too far to treat that here, but thin airfoil theory leads to, and then you calculate pressure distributions and stuff like that, and then you come to the conclusion that the lift curve slope is 2 pi. It's just what comes out of this theory, right? Sorry? For which kind of wings? This is only for a very thin airfoil, right? So it's not for a wing. This is for a very thin airfoil, like, say, 7, 8, 9, 10%. And it's 2 pi. If we would look at the very thick airfoils like you use in wind energy, right? So if you have a wind energy, a wind turbine blade, then at the root you have very thick airfoils because you need strength and stiffness, right? So there's very thick airfoils, and then this is not 2 pi, but it is much more. Then it's much steeper, this lift curve slope. Okay. Shall we do this? Well, let's skip that for a moment. We will have enough problems already, also in the studio classroom. So I'll skip this. Okay. So we have this wing concept, you know. We have a wing. There's the effect of the wing is that there's a wing vortex and we have induced drag. Okay. But now, if compressibility comes in, what happens? So here we have this wing here, and then they have this critical Mach number of 0.7. So somewhere on the airfoil, somewhere on this wing, we have a Mach is 1 at the flow of Mach crit is 0.7. If we now sweep the wing like this for 40 degrees, then what really happens is that what the airfoil sees in this situation is in fact this velocity. There is of course also a velocity in span direction, but the effective velocity making the pressure distribution is not V, it is V infinity cosine lambda, which makes the M critical for this swept wing not 0.7, but 0.7 divided by cosine lambda is 0.91. Right, so by sweeping the wing, the critical Mach number increases. So you can fly faster with the swept wing without compromising this compressibility thing on the upper surface. Right, so at a higher Mach number, there is this Mach is 1 somewhere on the wing. Yeah. Does it decrease the lift? No, in fact, it does not decrease the lift. Sorry, one?
Why don't all planes fly up to 60, for example, degrees swept wing?
Why don't all? Because sometimes it's not necessary. I mean, if you look at the construction and so, it's more difficult. So if you do not have compressibility effects, the best thing is to do it like this. Right? Because there still is a velocity like this. Just the incoming velocity is still the same here as in both cases. What you could always also see is that if you have a thickness here, then in fact, if you look at this, if we go back a little bit, if you look in this direction, then the airfoil will be thinner. Right? If you cross an airfoil with this thickness, and you do not cross it perpendicular, but you do it in an angle, like this, then it's in fact not this one, but it is this one. Right? So another way of looking at it is the fact that the airfoil, or what the velocity sees, is an airfoil which is longer and thinner. And we've seen that a thinner airfoil has lower supervelocities at the upper surface and has a higher critical Mach number. So either way you look at it, the critical Mach number is going up with this swept wing. So by sweeping the wings of a subsonic aircraft, the drag divergence is delayed to higher Mach numbers, because that is what it's all about, of course. You don't want to get into this drag divergence when the CD goes up and you have to put in a lot of fuel. Yeah. Sorry, what? The benefit of a delta wing is the fact that it has a large vortex from the which creates a lot of lift, because the velocities here are high and the lift, the pressures are low. So that's a little bit different concept than a general, and these are very thin as well, like this, very sharp here. So it's a little bit different concept, because this vortex that comes from the leading edge gives a very vast vortex. If you look at from this side, then you will see something like this. And so this gives very, very low pressures. This is the lift that is associated with it. Okay, but it's a little bit different then. But you see that you would go and use delta wings, because they all also have sweep, of course. You would use delta wings whenever you go to compressibility. Before that, it's not necessary. It's even detrimental, because delta wings have a low aspect ratio. And if you have a low aspect ratio, then of course your induced drag is higher. So for a subsonic aircraft, you just need a high aspect ratio for a low CD induced. Okay. So if we now look at the minimum CD of an airfoil that is 4%, 6%, and 9% thick, then this drag divergence comes in somewhere, right? So for a 4% thick airfoil, nothing so much happens here. There's no very significant increase in CD if I go beyond Mach 1. If I have a 6% thick airfoil, then of course we see here the drag divergence, and for a 9% thick, we see it here more prominently. Right? So stay away from this part here, because you need a lot of fuel. Now if we look at this 9% thick airfoil, put it in different aspect ratio wings, then we see this. Here, this is A, we see still this drag divergence, because virtually there's not so much sweep, of course. Here is moderate sweep and here is more sweep, and you see that this is what happens. In C, this 9% thick airfoil, what without sweep would have a very low drag divergence, is now having a drag divergence somewhere here. It goes from here to there, which is quite significant if you do that. If you look at it in terms of speed in cruise, then this is quite significant, and this all because of the sweep. Now, if we look at total drag of a wing, then the CD of a wing is the CD of the profile plus the term for the induced drag. If we look at a profile, then of course the CD is the part of the friction in the total CD, the part of the pressure drag, and part of, if we are in a compressible flow, is the wave drag. I will not say much about this wave drag, and we will not talk about it so much. This wave drag is coming from shock waves. If you have a shock wave, then there is an increase in pressure over the shock wave, and this increase in pressure has a component in the drag direction. So that's whenever you have a shock, then there is a wave drag associated with that. We don't go into that in much detail. Okay. Flaps. So now we have a wing. We can fly it in compressible and incompressible situations. We know what to do and how to calculate that. But now that's all about cruise, right? So if we want to take off and land, then we need something else. Because what happens if you approach, then you would like to, I mean, if you fly with 900 kilometers an hour, you would not land with 900 kilometers an hour, right? It is, you just don't do that. So you would like to lower your velocity. But there is a certain weight you have to carry, right? So this lift should be more or less in balance with the weight. But when you go down in velocity, then you need something else to carry this weight, which is okay when you fly a lot. If you look at W is L is CL times half rho V squared times S, this is more or less fixed, unless you dump a few passengers in cruise, but it's more or less fixed. And this changes, of course, if you lower V. And if you lower V, it goes with V squared, so that's quite a bit. So what you can do to more or less effectively go down and have this more or less balanced, then you can change this one, and you can change that one. If you have a fixed wing without any flaps and slats, then this is, of course, also fixed. And then the only thing you can do to counter the velocity going down is to increase the CL. And how would you increase the CL? Well, if you look at the lift curve, then your cruise lift will be right here, and to go up in lift is like this. So you just do like this with your wing, and then you go up here. So the CL increases, this goes up, and then you can lower V. Well, from this equation, of course, you can make an equation for the stall velocity, because this is, of course, something that you should avoid. Because no matter what you do here, increasing the angle of attack is not going to happen. The CL stays down, right? So you should not cross this one here. And in the cockpit, you see all kinds of signals when you approach this CL max. It's the velocity, the stall velocity that's associated with this point here is called the stall velocity, right? So this, the CL max is associated with this point here. And that is, of course, W divided by the half rho S CL max. That's only from if you rewrite this equation. Okay. So if the landing speed is decreased, you have to do something about the lift coefficient and the area. Now, of course, we've seen that if you have an airfoil and you increase the camber, you increase the curvature of the airfoil, then you increase the amount of air that is pushed downward. And because of the fact that you increase the air that pushes downward, the air will give a lift force up. So you increase the lift up if you camber your airfoil. And that's exactly what you do with a flap, because now, instead of having a straight airfoil with this camber, if you do it like this, then you have this camber right here, which means that you increase the downward velocity, which means that you have an increased lift, right? So increasing the camber means that you increase the lift up. And you will see that in the pressure distribution, because the pressure distribution is giving you this lift up. I mean, this is the idea behind it, but the real thing is that the pressure distribution changes in such a way that the net result is a increasing lift force. So whenever you extend a flap, or you just have a flap deflection, in this case it's just some pivot point here, and you have a flap deflection, then you go up. The entire lift curve shifts towards a higher value. Right? And this just because of this increase in curvature. And that can go quite far. Here it is 60 degrees. So, and again, here you do nothing on the area, the wing surface. It's only CL that you do. Okay, but so the net effect of deflection of a flap is that you push up the CL. Well, here you see some examples. A typical example. Here are the flaps here, and if we talk about devices on the leading edge instead of the trailing edge, we talk about slats. Okay, here you see slots between the flaps, which has also an advantage. Several types of flaps here, the split flap, and the upper surface stays constant, and this just comes out of the lower surface. You have a plain flap, like we discussed the previous slide. We have one with a fixed hinge somewhere here, and then a double slotted flap with a fixed hinge. I mean, here is a slot. When you deploy it, then here is a slot and there is a slot. There's, yeah. In the previous slide.
The plane flap.
Plane flap.
You will steer your plane downward, right? It's like a...
Well, if you deflect it like this, you forget this one. This is in the non-deflected situation, and this is in the deflected situation. No, it will go up. This is a positive flap deflection, right? And the curvature is, first it's like this, and then it's like that. And if you curve it more, right, then the extra lift vector will point upward. And if you deflect it up, then of course there is an extra lift vector downward, so then you go down. Okay. Here we have a slat with a fixed slot. Here we have a slat which is movable. This is a Kruger flap that is just that flaps out of the lower surface of the leading edge. And what happens here is that you change the resulting angle of attack. So would you have a CL alpha curve like this for a normal airfoil? Then if you have a trailing edge flap, then you would go like this, right? And if you would have a slat, then you would change the angle of attack for the CL max, so it goes like that. So if you do both, if you do nothing in the trailing edge, but you do it in the leading edge, then you would have something like that. So a slat extends the existing CL alpha curve, and a flap shifts the alpha curve, CL alpha curve, to a higher value. And the nice thing about all these slots, the nice thing about all these slots is the fact that you renew here we have a slot and here we have a slot. There was one remark to be made. If you have a curvature like this, then the pressure distribution is in such a way that you have a high velocity here and an adverse pressure gradient here. So the pressure goes up. And the negative Cp goes down, the pressure goes up. Which means that, just a moment, which means that if you do it like this, then the force on the boundary layer is also getting towards having it separate. So you need to take care that the flow does not separate over your flaps. But because if it does like this, then these are not effective anymore. So the nice thing about having these slots is that new air, not air from the boundary layer, new air is entering these slots here. And they give more energy to the flow that move along these surfaces. Boundary layer material coming from this gets new energy because this flow is not retarded by the friction. So there is new energy here so that the flow can follow this contour. I mean, it's the same as you look at ailerons, for instance. If you have a wing like this, and you have ailerons here, then sometimes you see on a wing these small, like of this type or of this type. These are called vortex generators. And would the flow separate in front of this aileron, then it's not effective anymore. So it's very hard to do this, right? So if you put in a vortex generator just in front, what happens is that there is higher velocity energy getting into the boundary layer so that the flow will not separate, but will follow the contour, right? So whenever you see these things, this is a precaution. Whenever the situation might be in such a way that it would separate here, then these vortex generators, they prevent from separation. And that's the same does these slots. It's new air with new energy coming down here. There was this question. Yeah. If you extend the flaps to reduce the critical Mach number, why would the critical Mach number be important at low altitude?
It's not important at all, but then you can't fly with high speeds if you extend the flaps.
If you extend, people, just a moment. If you extend the flaps, then you have very high velocities on the upper surface, but you fly at very low speed, right? So there's no critical Mach number involved there. If you would do that at cruise, then suddenly you would have very high drag because the result is a very high drag, and then you would need a lot of fuel. Okay. Since it's approaching lunchtime, this is the last thing that I would like to say to you. Good luck in the exam. On Wednesday, there is the studio classroom. We will do some problems there. So maybe I will see you there as well. Okay. Good luck.
Please visit our OpenCourseWare website for more information. See you at our next podcast.